In this video, we continue our discussion of derivatives of functions involving logarithms. I just thought this is a really interesting function. This is the function that we derived as an antiderivative of secant of x. So we know that when we take the derivative, we should get secant of x back. But we might be interested in what that function actually looks like. Might be interested in what the domain is, when the function is increasing and decreasing, what the second derivative looks like. And I mean, I know we can infer all of that based on the fact that this is an antiderivative of secant of x. But it might be interesting to start with the original function itself, not knowing that it's supposed to be the antiderivative of secant of x, and trying to derive that its derivative actually is secant of x. So let's look at this. And since we've got a logarithm, let's start by discussing the domain. We know that the domain of this function is the set of all x values where the absolute value of secant of x plus tangent of x is greater than 0. So I think we should be fine most of the time, but we need to know where that, because the absolute value is always almost always greater than 0, right? But we are concerned about when that expression is equal to 0, and also those x values when the original integrand is undefined. So let's look at that secant of x plus tangent of x. I like to rewrite it using my reciprocal identities. Secant of x is 1 divided by cosine of x, and tangent of x is sine of x divided by cosine of x. So this is really 1 plus sine of x divided by cosine of x. Now, in order to sort of understand the graph of secant of x plus tangent of x, it's helpful to look at the graph of 1 plus sine of x and the graph of a cosine of x. So sine of x looks like this. We know it repeats itself every 2 pi. So we start at 0, and then at pi over 2, we're at a max. And then we go back to 0, and then at 3 pi over 2, we're at a min. This is what sine of x looks like. And 1 plus sine of x is going to look just like that, but it's all the y values are increased by 1. So instead of having a range of -1 to 1, 1 plus sine of x has a range of 0 to 2. It's going to look like this. Same shape curve. And if we want to, we can go backwards a little bit. That maximum occurs at pi over 2. And from the last period, the minimum from the previous 2 pi is at -pi over 2. Then our 1 plus sine of x is going to look like this. Okay, so that's what we've got there. Now this is equal to 0. Oh, that's what sine of x, or 1 plus sine of x looks like. And then cosine looks like this. Cosine has a range of -1 to 1 as well. All of the interesting things happen at 1/4 of the period. We start at 1, and then we go to 0 at pi over 2. And then at pi, cosine has a minimum of -1. And then at 3 pi over 2, our cosine is 0. And at and 2 pi, excuse me, our cosine is 1. So roughly it looks like that. And if we go back to negative pi over 2, it starts at 0 there. So you can almost think of it as a shifted sine wave, a sine wave that starts at negative pi over 2 rather than starting at 0. So when I think about this, secant of x plus tangent of x, I say, okay, well, when is it equal to 0? It's equal to 0 whenever 1 plus sine of x is equal to 0. And so that's at 3 pi over, negative pi over 2, 3 pi over 2, and then 3 pi over 2 plus 2 pi, and so on. It's just going to repeat itself. It's going to be equal to 0 every time that we're at that 3 pi over 2. Actually, wait a minute. No, I'm sorry. I'm wrong. This fraction equals 0 when the numerator equals 0 and the denominator is non-zero. But we have to, so that was the mistake I made last time. I'm sorry. Have to be careful. At 3 pi over 2, 1 plus sine of x is 0. And cosine of x is also 0. So if I were evaluating the limit of this expression as we approach 3 pi over 2, what we would have is a 0 over 0 indeterminate form, because we'd have that 1 plus negative 1, which is 0, divided by 0. So let's look at the limit as x approaches 3 pi over 2 of 1 plus sine of x over cosine of x. Well, we can use L'Hopital's rule. L'Hopital's rule says take the derivative of the numerator and take the derivative of the denominator. And then if this function is continuous at that point, you plug in that x value, and then that will be the value of the limit. And this one is continuous at 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2, we know to be negative 1. So we just get 0 divided by negative 1, which is 0. So the limiting value of this function as x approaches 3 pi over 2 is 0. But the function itself is actually undefined there because we've got a 0 over 0 indeterminate form. So this secant of x plus tangent of x and I'm going to call that g of x, is undefined at x equals 3 pi over 2 plus 2 pi n, where n is any integer. Yes, it has a limit of 0 at all of those values. Okay. And then we say, okay, well, so that was one potential area of concern, because we're not allowed to take the logarithm of 0. And then this expression is also undefined whenever this denominator is 0 and the numerator is non-zero. So this denominator is 0 at all of the multiples of, or the odd multiples of pi over 2. So at pi over 2 and 3 pi over 2 and 5 pi over 2 and 7 pi over 2 and then negative pi over 2 and negative 3 pi over 2. So this function actually has an asymptote at all of these other zeros of our cosine function. So at pi over 2 plus 2 pi n, for where n is an integer, this function will have asymptotes. So we'll have vertical asymptotes. When the numerator is non-zero and the denominator is 0. Let's say which happens at x equals pi over 2 plus 2 pi n. Because if at x equals pi over 2, the numerator is approaching, or the numerator is approaching 1, 1 plus 1, excuse me. Sine of pi over 2 is 1, so we have 1 plus 1, which is 2, and then the denominator is 0. So you've got the 2 over something that's approaching 0. So that is either going to be plus or minus infinity. As we approach pi over 2 from the left, this expression is going to approach positive infinity because we've got 2 divided by a tiny positive number. And then as we approach pi over 2 from the right, we're gonna have 2 divided by a tiny negative number, so the function would approach negative infinity. We'll say the limit as x approaches these guys from the left, positive infinity, and then the limit as x approaches those vertical, or those that vertical asymptote from the right is negative infinity. And again, that's because I'm just thinking I'm taking that positive number, that number that's approaching 2, and then I'm dividing by a tiny positive number on the one side, which gives us a very large positive number, or a tiny negative number on the other. So that gives us a large negative number. So these correspond to removable discontinuities. At x equals 3 pi over 2 plus 2 pi n, and the limiting value, which is 0, because of that calculation. And then we've got these vertical asymptotes here and here. So if I want to graph this secant of x plus tangent of x now, we've got an asymptote at negative pi over 2, I think. Is that right? Here's pi over 2. Here's pi. Here's 3 pi over 2. And the asymptote is at pi over 2. And then our function is approaching 0 here. I think this is actually supposed to be one of the zeros. It's at negative pi over 2. And then at negative pi, we're here. And then at negative 3 pi over 2, we have another asymptote. So now if I want to graph this, g of x equal secant of x plus tangent of x, which is the same as 1 plus sine of x divided by cosine of x, what it will look like is this. As we approach pi over 2 from the left, our function values go to infinity. So it'd look roughly like that. And then as we approach pi over 2 from the right, our function values go to negative infinity. And then this thing repeats. We're going to see the same thing there and the same thing there. So that is g of x equals secant of x plus tangent of x. Now, this function that we started with involves taking the natural log of the absolute value of that. The absolute value of that is going to look very similar. When the function is positive, it's going to have those same values. It's going to be positive. But when the function is negative, it's going to look like that. So this is, I'm just going to call this g star of x. This is the absolute value of g of x. And then we're going to take the logarithm of this. Now, in order to think about what the graph of the logarithm of that should look like, it's helpful to look at the graph of just natural log of x in general. We know that natural log of x approaches negative infinity as x approaches 1 from the right. And then as x goes to positive infinity, natural log of x goes to positive infinity. This graph is a little bit misleading. The slope is 1 over x. So it actually sort of flattens out as x gets very large. This looks like it's growing much faster than it actually is. But x does go to infinity as x goes to infinity, natural log of x does go to infinity. It just goes to infinity very slowly because the slope is just 1 over x. You say, okay, with that in mind, what's going to happen to the natural log as the y values on the graph of the absolute value of secant of x plus tangent of x go to infinity? If I take the natural log of something like this, well, I'm going to get something that's also going to infinity. Now, as what's inside approaches 0, then my logarithm should approach negative infinity. So at these removable discontinuities of this secant of absolute value of secant of x plus tangent of x, our logarithm should have asymptotes. So those removable discontinuities correspond to asymptotes of the function of interest. And as we approach 0, the y values are going to go to negative infinity. And that should happen from the left and the right because we're taking the logarithm of a tiny positive number in either case. So the y values should go to positive infinity on either, or excuse me, negative infinity on either side here and here. And then as we approach the asymptotes of the secant of x plus tangent of x, we're taking the log of a very large positive number. So the limit as x goes to pi over 2 plus 2 pi n of our function should be positive. So I think what I'm expecting is well, something that does that there and there, but then at all the multiples of pi at 0, pi, 2 pi, negative pi, we might want to evaluate the function there and see what it looks like. So secant of x plus tangent of x is 1 plus sine of x divided by cosine of x. If we evaluate that at n pi. I've got 1 plus sine of n pi divided by cosine of n pi. Then sine of n pi is 0, where n is an integer, of course. So this is going to be a 1 in the numerator, and that cosine is going to alternate between -1 and 1. So we got cosine of 0 is 1, cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1. It just keeps going back and forth. So this is actually 1 divided by -1 to the n. So we just end up with a -1 to the n. We take the absolute value of that, we get 1. And then we take the natural log of 1, and so we get 0. Natural log of 1 is 0, e to the 0 is 1, right? So these function values for our f of x graph should be equal to 0 at all those multiples of pi. And then as we approach this negative pi over 2, our function should go to negative infinity. And as we approach the pi over 2 plus 2 pi n, our function should go to positive infinity. We're going to see that. So it kind of reminds me of the tangent graph or the cotangent graph, but it sort of changes directions, doesn't it? So that's our graph, I think. Is that correct? Maybe it's not. So we're taking the natural log of a large number, should be large. Natural log of a tiny positive number, so it should be very small and negative. I think that's right. Let's look at a graphing calculator and see what that looks like. So this is the graph of g of x equals 1 plus sine of x divided by cosine of x. But Desmos is a little bit misleading. It does not include those removable discontinuities. But we know that the function has removable discontinuities at 3 pi over 2 because the numerator and denominator are both 0 there. So we should have a removable discontinuity here, and then we should have that repeating every 2 pi. So I've actually plotted some points. This is just that g of x equals secant of x plus tangent of x. And then we had asymptotes at all of the pi over 2, x equals pi over 2 values, plus or minus 2 pi as many times as we want. So all those vertical asymptotes. And then we said, rather than looking at g of x, let's look at the absolute value of g of x now. The absolute value of g of x looks like that. And so we're really taking the logarithm of that. And we're saying, okay, well, what should the logarithm of that be like? Well, this is what I did on my paper. I said it should look something like this. As we approach those removable discontinuities of the absolute value of g of x, we should approach negative infinity. And then as we approach the original vertical asymptotes of that g of x, or the absolute value of g of x, I think we should go to positive infinity. I don't know if that's actually going to happen, but let's see. And that's what the graph looks like on Desmos. So I think that we're seeing sort of that same pattern. So to go to negative infinity wherever the original or the argument was approaching that removable discontinuity, and positive infinity over here and here. It's like a fly in my environment. I don't really know why Desmos is graphing all of these values, the y values on the graph. But maybe the y values are getting very, very close to that. Or the points on the graph are getting very, very close to those asymptotes, so close that it's almost indistinguishable from the asymptotes. But I think that has the same general shape as what I've drawn here. It just gets closer to the asymptote faster than I imagined it would. Now, if we take the derivative of that, we should get secant of x, because we know that this is one of the antiderivatives of secant of x. We can do that on paper. And then we want to compare that derivative, or compare the graph of secant of x to the graph of this, its antiderivative as well. So this is our hand-drawn sketch of natural log of the absolute value of secant of x plus tangent of x. We saw on Desmos that the function seems to approach these asymptotes faster than the way I have it drawn here. Like there's just a smaller range of y values before it's almost sort of on top of the asymptote. As we go from this 0 of the function to that asymptote. They almost have like these two curves coming together and those two curves coming together. But it's just because the function is very, very close to that asymptote, like very, very quickly, as far as like the rate of change as y increases. Now, if we want to compute the derivative of this, we can use the chain rule. Well, the derivative of natural log of the absolute value of a function is just 1 over that function. And we know this because when we looked at the natural log of the absolute value of x, we inferred that its derivative was 1 over x. And then when we looked at natural log of the absolute value, or natural log of negative x, we got 1 over negative x times -1, the negatives canceled. So in general, the derivative of natural log of the absolute value of x is 1 over x. So the derivative of natural log of the absolute value of secant of x plus tangent of x can be computed using the chain rule. So it's just 1 over secant of x plus tangent of x times the derivative of the inside. And the derivative of the inside is the derivative of secant, which is secant of x times tangent of x, plus the derivative of tangent of x, which is secant squared x. And if we want, we can just write that as itself over 1. Then we multiply straight across and we have this divided by this. But we see that both of these terms have a factor of secant of x in common, so you can factor that out. You have secant of x times tangent of x, that gives you that first term. And then secant of x times secant of x, which gives you the second one. And we're dividing all of that by this secant of x plus tangent of x. And that's the same thing. It's multiplication, or excuse me, addition is commutative, right? A plus b is the same as b plus a. So those are the same. And our derivative is secant of x. say, okay, well, if the derivative of this function is secant of x, well, what does that look like? Well, I don't actually know what secant of x looks like off the top of my head, but I know what cosine looks like. And with a cosine graph, I can use that to infer what the secant graph looks like. So cosine repeats itself. Now cosine is 1 at 0, and then it's 0 at pi over 2, and then it's -1 at pi, and then 0 at 3 pi over 2, and then it's 1 again at 2 pi, and it repeats. This is my cosine function. And that continues in both directions. So it's max, 0, min, 0, max. And the secant graph has asymptotes every time the cosine graph is, or cosine function is 0. So I'm going to draw some asymptotes here. I'm just using my cosine graph to guide my secant graph. And then secant of x is 1 divided by cosine. So whenever the cosine is 1, secant is 1. Whenever cosine is -1, secant is -1. The graph looks like this. As we approach negative pi over 2 and pi over 2, the y values on the cosine graph are tiny positive numbers. 1 divided by a tiny positive number is a large positive number. So the secant looks like that. Here, as we approach pi over 2 and 3 pi over 2 from the right and left respectively, cosine is a tiny negative number. 1 divided by a tiny negative number is a large negative number. And so we get these sort of U-shaped things, and the pattern repeats. So the claim is that these tell us the derivative of this function. Okay, so that's y equals secant of x. The claim is that that's the derivative of this green function. Let's make sure it's true. Okay, well, what am I expecting? When I look at this green function, on this branch from negative pi over 2 to pi over 2, it's increasing, right? And so I would imagine all the slopes are positive. And we see that they are. All the y values on the graph of secant of x are positive. And it has actually a minimum slope at x equals 0. That minimum is 1. So here I should have a slope of 1. So if I drew the tangent line, it would just be the graph of y equals x. And that's what I see. And then on this next branch, it's going to be very similar, but all of these, all the tangent lines are decreasing, right? If I draw a tangent line, the y values decrease on those graphs as we look at the y values from left to right. So the slopes are going to be all negative, which is consistent with our value of the secant of x. Secant is negative here. And sort of the maximum slope in absolute, well, the maximum of these y values on the secant graph is -1. So we're going to have a slope of -1 here. So basically what it is it's going to be very, very, very steep. And it gets less steep and less steep and less steep until it gets to a slope of -1. And then it starts getting steeper again. Then it's like it goes from -1 to, negative 1.5, and then -2, and eventually, so the slopes just keep getting steeper and steeper. So sort of the minimum steepness of our slope occurs here, but it's actually the maximum value of that secant. But it just seems like it's not a maximum. It feels more like a minimum because when we compare it to the steepness of the rest of the graph on that branch, it's not as steep. It's the least steep point, but it's technically at a maximum. So that's what we've got there. And then we're just gonna have that pattern repeat. So we have a very, very steep positive slope. Then the slope just sort of decreases until it gets to 1. And then the slope increases from as we move from this point from here to here. And then this is a very large magnitude negative slope. Then it gets less steep until the slope is -1, and then it gets increasingly steep as we approach that other asymptote, and that pattern repeats. And you say, okay, well, what about the second derivative? What if I took the derivative again? Well, if I took the derivative again, the derivative of secant of x is secant of x times tangent of x. And the sign of that is determined by the sign of secant and the sign of tangent and how those compare to each other. Now, if I graph those on the same set of axes, the tangent has asymptotes at every time the cosine is 0. So does the secant, right? At all the odd multiples of pi over 2. It's going to graph tangent now. Tangent looks like this. And we're going to take those values and we're going to multiply them by the values of the secant function. So if I sort of line those up, on the interval from 0 to pi over 2, secant is positive and tangent is positive, so the derivative is positive. On the interval from pi over 2 to pi, secant is negative and tangent is negative, so the secant times tangent is positive. If you want, you can write that as 1 over cosine of x times, times sine of x over cosine of x. So you can call that sine of x divided by cosine squared x. So we're going to have asymptotes, the same place that the tangent and the secant have asymptotes at all of those odd multiples of pi over 2. And then the SIGN sign of this is determined by this SIGN sign of sine of x. So f double prime will be positive when x is between 0 and pi, because we know what the sine graph looks like. And then that's going to be negative when x is between pi and 2 pi. But we still have those asymptotes at all the odd multiples of pi over 2. So what I think I'm going to see here, we have 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. See, our second derivative is sine of x divided by cosine squared x. Sine is positive, positive, and negative, and negative. Cosine squared is always positive. to positive, positive, negative, negative for our sign of x double prime. So we would say the graph is concave up, and then we have concave down and concave down. Now let's see if that's consistent with what we see on this green graph. Is it concave up and concave up? It sure is. And then concave down and concave down it is. But we've got those asymptotes there. So whenever you look at this, you might say, that's not what the graph looks like. You're right, it doesn't. On the interval from 0 to pi over 2, the function is increasing and concave up. So it just looks like this, just like that right hand. And then on the interval from pi over 2 to pi, the function is decreasing and concave up. So it's that side. And then on the interval from pi to 3 pi over 2, it's decreasing and concave down. So it looks like that. And then on the interval from 3 pi over 2 to 2 pi, it's increasing and concave down. So it looks like that. So like those are the little curves I draw for concave up and concave down every time. But if the function is just increasing or just increasing there, we just got either something that looks like the left half or the right half of each of those little curves. All right, so I think that was kind of interesting. We were able to take the derivative of this using the chain rule, then analyze the function's domain by looking at that argument of the natural logarithm. We graphed secant of x plus tangent of x, and then we graphed its absolute value, which looks like that. And then we said those removable discontinuities correspond to vertical asymptotes of our function. Our function is the one graphed in green here. Because as the argument, it goes to 0 from the right. So the y values and on this graph are approaching 0 and they're tiny positive numbers. The logarithm should go to negative infinity. And as what's inside the logarithm goes to positive infinity, the logarithm itself goes to positive infinity. And that's why we get those asymptotes. So I hope that was fun. I hope you enjoyed that. I think the graphs are pretty. A little bit inconsistent with what we see on Desmos, but I think the reason is on Desmos, we can see that the graph itself actually approaches those asymptotes faster than I have it shown here. So let's look at that before we end the video. So those are all those removable discontinuities of the absolute value of g of x, that's secant plus tangent. And they corresponded to vertical asymptotes. And the log of the absolute value of secant of x plus tangent of x approaches the asymptotes of the original function. The function values on our graph go to infinity, and those asymptotes of the original function, and everywhere the original function, that again, the absolute value of g of x, at all of those removable discontinuities, the logarithm of that has a vertical asymptote. I didn't actually sketch that, but we could have sketched those vertical asymptotes there. And then we would see that our function is approaching those asymptotes. And this is what it looks like when I added those asymptotes at the removable discontinuities. I made the asymptotes for the removable discontinuities orange dotted lines, and then add asymptotes at the x values corresponding to the removable discontinuities, and x values corresponding to the asymptotes of the original g of x, or the absolute value of g of x, are in white. But we see the branches of our log of the absolute value of secant of x plus tangent of x approach those asymptotes, and it kind of has that same shape roughly as a tangent, the branch of a tangent graph or the branch of a cotangent graph, but it just keeps switching, it keeps alternating directions. And I think that's pretty cool. I think it's a pretty graph. I like our graphs on paper better. but I think this is supposed to be a little bit more accurate as far as the y values are concerned. Not really sure about these y values down here, but I think the y values on the original graph probably really approach that those asymptotes faster than the ones on my graph on paper.